The heat reaches you before the door opens. Even through layers of wool, leather, and sweat-soaked cloth, the boiler room announces itself from the corridor outside. A deep, metallic roar vibrates through the floorboards beneath your boots. Steam hisses from unseen valves somewhere behind the walls. The air smells of coal smoke, burning oil, wet iron, and something else underneath it all, something human. The shift has already begun. Inside the factory, the temperature climbs past what most bodies can tolerate for long periods. Boiler walls glow dull red in sections where the fireboxes burn hardest. Gauges tremble under pressure. Water pumps hammer without pause. Men move through the haze carrying shovels, tools, and ash buckets with mechanical rhythm, because hesitation inside this place is dangerous. And the boilers never stop demanding fuel. Every minute the furnaces cool, production slows. Every drop in steam pressure threatens the machines above. Rolling mills, presses, turbines, conveyor systems, entire industrial floors dependent on the force generated in this room. Thousands of workers above ground may never see the boiler floor, but their world depends entirely on it. So you shovel, hour after hour. Coal dust fills your lungs until breathing itself feels abrasive. Heat strips water from the body faster than it can be replaced. Shirts stiffen white with dried salt. Some workers collapse quietly against the walls during shifts. Others continue until their hands blister open around steel tools. And still the boilers consume more. Because this factory was not built around human endurance, it was built around pressure. Pressure strong enough to power an industrial empire, drive steel production day and night, and turn fuel into motion at a scale the 19th century once considered impossible. But hidden beneath that achievement was another reality entirely, a workforce trapped inside one of the hottest industrial environments ever created, feeding machines that could not survive without them. The question was never whether the boilers worked. The question was how long the men beside them could. Before the great boiler factories existed, industry moved at the speed of muscle, water, and weather. Production depended on rivers turning wooden wheels. Mills slowed when currents weakened. Workshops halted when winter froze transport routes. Iron forges relied on charcoal fires that could not sustain the temperatures needed for continuous heavy manufacturing. Entire economies remained trapped within the limitations of geography and human endurance. A blacksmith could shape iron, a foundry could cast components, a watermill could grind grain or drive simple machinery. But none of these systems could sustain the immense, uninterrupted mechanical force demanded by the industrial age that was beginning to emerge. The problem was not invention, it was scale. As cities expanded through the 18th and 19th centuries, populations surged beyond what older production systems could support. Railroads demanded thousands of miles of steel track. Steamships required stronger engines and heavier plates. Urban construction consumed iron faster than traditional furnaces could produce it. Textile mills multiplied across industrial regions, each requiring constant motion to remain profitable. Factories no longer needed occasional power. They needed permanent power. Water wheels offered strength, but only where rivers allowed. Animal labor was expensive, slow, and biologically limited. Human labor alone could not drive the increasingly massive machines being introduced into industrial production. Even early steam engines remained constrained by inconsistent heating systems that struggled to maintain stable pressure over long periods. The entire industrial world faced a single bottleneck: how to generate enough controlled energy to keep factories alive continuously. The answer emerged through boilers. At first, they were crude systems, thick iron vessels heated by coal fires, designed to convert water into steam, powerful enough to move pistons and rotational shafts. Early boilers were inefficient, unstable, and notoriously dangerous, but they offered something no previous system could provide: independence from natural rhythms. A boiler did not care whether rivers froze. It did not depend on wind. It did not weaken from exhaustion. As long as fuel and water entered the system, steam pressure could continue building indefinitely. That changed everything. Factories were no longer tethered to geography alone. Industrial centers could expand inside crowded cities where labor was abundant and transportation networks converged. Production schedules extended into night hours. Entire districts began operating around continuous mechanical cycles powered by centralized steam systems. But this transformation created another problem immediately. Boilers consumed unimaginable quantities of fuel. Coal became the dominant answer because it burned hotter and longer than wood, and industrial nations possessed vast underground reserves waiting to be extracted. Yet coal introduced its own chain of labor demands. Mines had to produce continuously. Rail systems had to transport fuel without interruption. Workers inside boiler rooms had to feed furnaces manually, often for shifts lasting 12 or more hours. The machines solved the energy crisis by creating a labor crisis beneath it. Inside early industrial factories, boiler rooms became the hidden heart of production. They were often built below ground or at the rear of facilities, isolated from administrative offices and separated from finished goods. Visitors rarely saw them. Investors focused on output above ground. Engineers celebrated the efficiency of steam-powered machinery. Newspapers praised industrial expansion. But beneath the visible machinery was another industrial world entirely. Dark corridors lined with pipes. Firebox doors slamming open in bursts of white heat. Coal dust drifting permanently through the air. Men moving through temperatures that could exceed survivable limits for extended periods. The boiler worker occupied a strange position inside industrial society. Without him, the factory stopped. Steam pressure collapsed. Production failed. Yet his labor remained largely invisible because it existed beneath the glamour of industrial achievement, and the work itself was brutal in ways that reached beyond exhaustion. Before automated fuel systems existed, coal had to be shoveled manually into furnace mouths with relentless timing. Too little fuel reduced steam pressure. Too much fuel destabilized combustion and increased explosion risk. Ash had to be removed continuously to maintain airflow beneath the fire grates. Water levels inside the boilers required constant monitoring because overheating exposed metal surfaces directly to furnace temperatures, weakening the structure from within. There was no margin for inattention. A single error inside the boiler room could destroy entire sections of a factory. Boiler explosions became one of the defining industrial disasters of the 19th century. Weak rivets failed under pressure. Poorly maintained systems ruptured without warning. Superheated steam expanded instantly upon release, tearing through walls, machinery, and human bodies with catastrophic force. Yet factories continued building larger boilers because demand continued growing. Steel mills required greater pressure to drive heavier rolling equipment. Textile complexes expanded into multi-floor operations dependent on centralized steam systems. Shipyards needed more powerful engines for transoceanic vessels. Cities themselves became steam-powered organisms dependent on energy systems hidden behind brick walls and underground tunnels. The world was industrializing faster than older power systems could support, and so the boilers grew hotter, larger, more pressurized, more dangerous. By the late 19th century, some industrial boiler rooms operated continuously for months at a time. Crews rotated through shifts while the fires remained alive permanently. Entire buildings were designed around heat management because the boilers generated temperatures capable of warping structural steel and cracking masonry over time. The factory became a living furnace, and inside it, boiler workers existed in conditions closer to controlled survival than ordinary labor. Your body adjusted or it failed. Skin remained coated in sweat and soot. Lungs filled gradually with coal dust and combustion residue. Dehydration became routine. Hearing damage accumulated from the constant percussion of pumps, valves, and steam discharge. Sleep patterns fractured under rotating shifts that ignored natural daylight entirely. But industrial society viewed this suffering as necessary, because the alternative was stagnation. Without the boiler room, there was no modern factory. Without the factory, there was no industrial empire. And so the problem before the machine was never simply power generation. It was humanity's attempt to build a civilization capable of operating beyond the limits of nature, then forcing workers to survive inside the systems that made that ambition possible. The boiler room did not emerge because industry admired heat. It emerged because entire economies became trapped inside a growing addiction to steam. Before electricity spread across industrial nations, power had to be created physically, immediately, and locally. Factories could not rely on distant grids. Elevators could not rise without pressure. Textile mills could not turn thousands of spindles through human muscle alone. Steel furnaces required blast systems powerful enough to feed combustion continuously. Ships crossing the Atlantic needed propulsion independent of wind. Cities demanded pumping stations capable of forcing water uphill into expanding districts crowded with immigrants, tenements, slaughterhouses, and rail terminals. Steam became the bloodstream of industrial civilization, and the heart producing that steam was the boiler room. By the middle of the 19th century, industrial growth accelerated beyond anything earlier generations had imagined. New York climbed upward into vertical architecture. Chicago rebuilt itself after fire and transformed into a steel metropolis. Pittsburgh consumed mountains of coal to feed rolling mills and foundries. London buried itself beneath fog generated by millions of furnaces and industrial fires. Every new building, every elevator shaft, every machine shop, every steamship terminal increased demand for heat and pressure. The problem was scale. Early boilers were small and unreliable. They powered isolated workshops or river vessels. But heavy industry required something far larger. Factory owners needed continuous steam generation capable of running entire industrial complexes day and night without interruption. Downtime meant financial collapse. A steel mill losing pressure during production could destroy molten batches worth enormous sums. Textile factories depended on uninterrupted rotational motion across hundreds of machines connected through shafts and belts. Municipal heating systems required constant pressure during winter months, or entire neighborhoods froze. Industry demanded bigger boilers. Bigger boilers demanded more fuel. More fuel demanded more workers. The transformation accelerated after the American Civil War. Railroad expansion linked coal regions directly to industrial cities. Appalachian mines extracted enormous quantities of bituminous coal. Pennsylvania became one of the most important fuel centers on Earth. Rail cars delivered black fuel directly into factory districts, where boilers multiplied beneath warehouses, mills, hotels, government buildings, and ocean ports. Coal solved one problem while creating another. It burned hotter than wood and allowed enormous pressure generation, but it also produced ash, toxic smoke, sulfur gases, and brutal physical labor. Boilers capable of driving industrial machinery consumed staggering amounts of fuel. A large factory might burn dozens of tons each day. Ocean liners crossing the Atlantic required non-stop feeding schedules maintained by entire crews working below deck in suffocating heat. The machine demanded human bodies constantly. Industrialists understood this immediately. Many companies redesigned entire buildings around steam infrastructure. Boiler rooms were often placed underground to stabilize heavy machinery and isolate explosions away from public view. Thick masonry walls surrounded furnaces. Ventilation shafts carried smoke upward through towering stacks, visible for miles across industrial skylines. Pipes spread through ceilings and tunnels like arteries distributing pressure throughout factories. The boiler stopped being a machine. It became architecture. By the 1880s, engineering firms competed aggressively to design larger and more efficient systems. Companies like Babcock and Wilcox, Stirling Boiler, and Foster Wheeler introduced water tube boilers capable of operating at far higher pressures than earlier fire tube designs. Railroads installed massive steam plants to maintain repair facilities and terminals. Steel corporations constructed dedicated powerhouse buildings beside furnaces and rolling mills. Urban hotels advertised steam heating as proof of modern luxury, but every improvement increased danger. Higher pressure created more power, yet it also turned the boiler into a potential bomb. Poor welds, weak rivets, scale buildup, or operator mistakes could transform a factory basement into an explosion chamber. Entire buildings vanished during catastrophic failures. Boiler fragments traveled through walls with artillery-like force. Workers near rupture zones were often vaporized instantly. Still, industry accepted the risk. The alternative was stagnation. Industrial capitalism during the late 19th and early 20th centuries rewarded output above all else. Production quotas rose relentlessly. Factory owners calculated labor as a replaceable expense measured against operational efficiency. If a boiler room consumed workers through exhaustion, burns, or lung damage, replacements arrived continuously through immigration and poverty migration. Men entered industrial cities because agriculture no longer sustained them. Eastern European immigrants, black laborers escaping Southern oppression, Irish workers, Italians, and rural migrants poured into expanding industrial centers, searching for wages. Many lacked technical education, political protection, or bargaining power. Boiler rooms became employment reservoirs for those willing to survive extreme physical conditions, or those desperate enough. Training was often minimal. A young worker might learn furnace operation by watching older firemen for several nights before handling live combustion himself. Supervisors prioritized endurance over safety. Men capable of lifting coal continuously inside temperatures exceeding safe limits became valuable regardless of long-term health consequences. And the work never truly stopped. Factories operated around the clock because steam systems required stability. Allowing boilers to cool completely wasted fuel, damaged productivity schedules, and delayed manufacturing cycles. Night crews inherited the same heat as day crews. Men disappeared underground before sunrise and emerged coated in soot after dark. Their clothing carried sulfur and coal dust home into crowded boarding houses where industrial contamination followed entire communities. Meanwhile, cities above ground celebrated industrial progress. Newspapers praised skyscrapers, electrified rail systems, luxury hotels, steamships, and record-setting manufacturing output. Politicians described factories as engines of civilization. Engineers became symbols of modern achievement. Massive boilers represented mastery over nature itself. Human beings had learned to trap explosive pressure inside steel chambers and force it into useful labor. But hidden beneath that triumph stood the workers feeding the furnaces. The contradiction deepened during the early 20th century as urban infrastructure expanded further. Centralized steam systems began heating entire districts. Hospitals, government complexes, universities, and financial buildings relied on industrial boiler networks. During winter months, uninterrupted steam delivery became essential for survival in northern cities. Boiler rooms became invisible necessities. Most citizens never saw them. They experienced only the results: warm radiators, functioning elevators, illuminated buildings, efficient factories, moving trains, and industrial abundance. The furnace crews remained buried beneath streets, foundations, and engine halls where the physical cost of modernity stayed largely hidden from public life. World War I intensified dependence even further. Steel production exploded. Shipyards expanded rapidly. Munitions factories operated continuously. Boiler crews became critical industrial labor, sustaining wartime logistics. Coal consumption reached staggering levels. Entire rail networks existed primarily to transport fuel into industrial centers, where boilers transformed chemical energy into mechanical force. Then came the interwar years and the Great Depression. Economic collapse devastated workers, yet heavy industry still depended on steam infrastructure. Men accepted increasingly dangerous conditions simply to maintain employment. Safety inspections were inconsistent. Maintenance budgets shrank. Aging boilers remained operational far beyond intended lifespans because replacing them cost too much during economic crisis. This created a dangerous industrial landscape. Old pressure systems operated beside newer high-capacity units. Temporary repairs became permanent solutions. Corrosion spread inside neglected pipes. Boiler scale accumulated silently, reducing cooling efficiency and increasing rupture risk. Exhaust systems failed gradually, exposing crews to toxic gases over years rather than moments. By World War II, industrial steam reached another peak. Factories manufacturing tanks, ships, aircraft, and ammunition relied heavily on massive boiler plants. Workers endured punishing schedules under wartime production demands. Some boiler rooms operated continuously for years, with only brief maintenance shutdowns. Heat exhaustion, respiratory illness, and hearing damage became normalized industrial conditions. The world needed power faster than it needed protection. And beneath nearly every major industrial achievement of the steam age stood a furnace room where men fed coal into engineered fire without pause. Not because the work was admired, because civilization demanded the pressure. A boiler room is not a single machine. It is a system of controlled violence, contained inside steel and brick, where fire is disciplined into pressure and pressure is converted into motion. At its center stands the boiler itself, a massive steel vessel, often cylindrical or box-shaped, reinforced with riveted seams or welded plates depending on the era. Some units weigh several tons empty. Fully operational systems, filled with water, steam, and attached piping networks, become structures rather than machines. They do not sit inside buildings. They define them. The process begins with combustion. Coal, oil, or sometimes wood, is fed into a furnace chamber at the base of the system. In early industrial designs, this feeding is manual. A worker, often called a fireman, shovels coal into a burning grate. Each shovelful lands in a bed of fire already operating at temperatures high enough to glow orange-white at its core. The furnace door opens and closes in repetitive cycles, releasing bursts of radiant heat into the confined space. Inside, combustion temperatures can exceed 1,200 to 1,600 degrees Celsius, depending on fuel efficiency and airflow control. Above the furnace sits the water reservoir, separated by thick steel walls or a network of tubes. This is where transformation occurs. Heat rises violently through conduction and convection, transferring energy into the water. As molecules accelerate, they begin to separate from liquid form. Steam forms in pockets, then expands rapidly under confinement. Pressure begins to build. In many industrial systems, boiler pressure can reach 150 to 300 pounds per square inch in early designs, and far higher in later high-pressure water tube configurations, where specialized engineering allows safer containment of extreme force. But safety is always relative. Every increase in pressure brings proportional risk, because pressure is not static. It is stored energy. Once steam forms, it is directed through pipes, valves, and regulators into distribution systems. These pipes are insulated but never fully isolated. They vibrate constantly as high-velocity steam rushes through them. The sound is continuous, a low, distant roar layered with metallic ticking as pipes expand and contract under thermal stress. The entire system breathes. Valves regulate flow by opening and closing with mechanical precision. Gauge instruments track pressure levels, often using analog dials that flicker under vibration. If pressure rises too high, safety valves release steam into the atmosphere, producing sudden explosive hissing bursts that echo through boiler rooms like short-lived storms. The machinery connected to this system determines its purpose. In factories, steam drives pistons in massive engines. These pistons move in long, rhythmic strokes, converting linear pressure into rotational motion through crankshafts. That motion powers conveyor belts, stamping machines, textile looms, elevators, cranes, and ventilation systems. In urban infrastructure, steam moves water. Pump engines force water upward through city pipelines, overcoming gravity to deliver drinking water to upper floors of buildings and maintain sanitation systems below ground. Without constant pressure, entire districts would lose access to basic infrastructure within hours. In locomotives and ships, steam becomes propulsion. In rail systems, boilers feed engines that convert pressure into forward motion through pistons linked to wheels. In marine vessels, steam turbines or piston engines drive massive propellers that push through ocean resistance. Entire global trade routes depended on these pressure systems operating without interruption. But every part of this process carries risk. The furnace produces not only heat, but ash, carbon monoxide, sulfur compounds, and fine particulates that drift through the air. The boiler itself accumulates scale, mineral deposits formed from repeated heating cycles, which reduces thermal efficiency and increases stress on metal surfaces. If not cleaned, scale becomes an insulating barrier that causes uneven heating and localized failure points. Metal expands under heat. It contracts under cooling. This constant cycle creates fatigue in structural components. Rivets loosen. Weld seams weaken. Pipes develop microfractures invisible to the naked eye. Inside a boiler, failure rarely begins dramatically. It begins silently as microscopic stress accumulating over thousands of heating cycles. The soundscape reflects this instability. A functioning boiler room is never quiet. It contains layered industrial noise, the deep roar of combustion, the sharp hiss of steam release, the rhythmic thump of mechanical pumps, and the metallic groan of expanding steel. Workers learn to interpret these sounds instinctively. A change in pitch can indicate pressure imbalance. A sudden silence can indicate fuel interruption. A high-frequency whistle can signal valve malfunction. Smell is equally important. Coal combustion produces a dense mixture of sulfur, carbon, and ash. Oil-fired systems add a heavier petroleum scent. Combined with moisture from steam leakage, the air becomes thick, humid, and chemically active. It clings to skin and penetrates fabric. Workers rarely leave the boiler room without carrying its scent with them. Temperature defines everything. Floor-level heat can remain relatively stable, but as one approaches furnace openings or pipe junctions, temperatures rise sharply. In poorly ventilated systems, ambient air can exceed safe human tolerance limits. Sweat evaporates instantly. Breathing becomes labored. Metal surfaces become too hot to touch without protection, yet must be handled for maintenance, adjustment, and repair. Vibration is constant. Large boilers are anchored into concrete foundations to absorb structural movement, but they never achieve full stability. Steam pulses through pipelines create microshocks that travel through the entire structure. Over time, buildings develop their own response to these vibrations, subtle architectural fatigue that engineers must constantly monitor. The rhythm of operation is relentless. Fuel is added, pressure rises, steam is distributed, valves regulate flow, ash is removed, water levels are adjusted. Then the cycle repeats, often for 12-hour shifts or longer. In large industrial systems, multiple boilers operate in staggered cycles to ensure continuous output, meaning there is never a moment when the system is fully at rest. This is the hidden truth of the boiler room. It is not powered by a single ignition point. It is powered by uninterrupted human attention. Operators monitor gauges, adjust fuel feed rates, inspect valves, and respond to anomalies in real time. Even automated systems introduced later in industrial history never fully removed the need for human oversight. Machines could regulate pressure, humans interpreted failure, and failure was always present. Because inside every boiler lies a contradiction. The more efficiently it converts heat into power, the closer it moves toward catastrophic instability. That is the nature of controlled pressure. It is always trying to escape. There is a point inside a boiler room where heat stops feeling like temperature and starts feeling like pressure against the body itself. Workers learned this early, not through instruction, but through survival. A boiler operator's shift begins before the furnace is fully awake. The first hours are adjustment, checking water levels, inspecting gauges, opening ash pits, and feeding the initial coal that brings the system back to full combustion. But once the system stabilizes, time changes shape. Minutes stop behaving like minutes. They stretch under heat, noise, and repetition until the entire shift becomes a single, continuous physical experience. The human body was never designed for this environment. Skin dries and cracks under constant radiant heat. Eyes sting from coal dust and steam condensation. Lungs carry fine particles that settle deep into tissue over years of exposure. Even when masks or damp cloths are used, they cannot fully block the mixture of ash, sulfur, and chemical residue suspended in the air. And yet, the work continues, because the boiler cannot be left unattended. A moment of inattention becomes a mechanical event. Water levels drop too low and expose metal tubes to direct flame, risking rupture. Pressure rises too quickly and safety valves struggle to release enough steam. Fuel feeds become uneven and combustion destabilizes. Each variable connects to another in a chain that never allows rest. Workers begin to move by instinct. They learn the exact sound of stable pressure versus unstable pressure. They recognize when a valve is slightly misaligned by vibration alone. They can tell, without looking, when coal distribution is uneven in the furnace bed. Their senses become extensions of the machine, but the machine never becomes gentle. In older industrial facilities, boiler explosions were not rare events. They were expected risks managed through engineering rather than eliminated. A single structural failure could release superheated steam and shrapnel with explosive force strong enough to destroy entire boiler rooms and adjacent factory sections. Walls collapsed. Steel panels tore free. Workers near the center of rupture rarely survived. Even smaller failures were devastating. Steam leaks under high pressure cut through skin like invisible blades. Pipe bursts created instant scald zones where survival was impossible within seconds. Furnace backdrafts sometimes ignited sudden fire surges that filled enclosed rooms with flame and smoke. These were not accidents in the modern sense. They were system outcomes. Maintenance reduced risk but never removed it. Every repair extended the life of a machine already operating near material limits. Every inspection was a negotiation with fatigue, corrosion, and time. And yet, industrial demand never slowed. In fact, it intensified. As cities expanded and electrification began to replace steam in certain applications, boiler systems were pushed into heavier industrial roles: steel production, chemical plants, district heating, and large-scale manufacturing. Instead of disappearing, boiler rooms were consolidated into fewer, larger, more powerful installations. Bigger systems meant fewer operators per unit of output, but also greater consequences when something failed. A single modern industrial boiler plant could support an entire district or factory complex. If it went offline, production stopped everywhere it supplied. Entire urban sections could lose heating during winter. Manufacturing lines could freeze mid-process, destroying materials and equipment. The pressure shifted from individual boilers to entire networks, and workers became guardians of infrastructure no longer visible to the public. By the mid-20th century, automation began changing the nature of boiler operation. Mechanical regulators, pressure sensors, and later electronic control systems reduced the need for constant manual adjustment. Fuel feed systems became partially automated. Combustion efficiency improved. Safety mechanisms became more responsive. But automation did not eliminate labor. It changed its location. Workers transitioned from direct furnace operation to monitoring roles, watching gauges, adjusting control panels, and responding to alarms instead of manually feeding fire. Yet even in automated systems, human presence remained essential. Machines could detect anomalies, but they could not always interpret them correctly under complex conditions. And when automation failed, humans returned immediately to the furnace, because no system trusted itself completely. The decline of traditional coal-fired boiler rooms began in many regions with the rise of electrical power grids and gas-based heating systems. Electricity decentralized energy production, reducing the need for localized steam generation. Natural gas offered cleaner combustion with less ash and lower maintenance requirements. Nuclear and hydroelectric power shifted industrial energy dependence further away from coal. But transition was uneven. Many industrial facilities continued using boiler systems well into the late 20th century. Some still operate today in modified forms. Older plants were not always replaced immediately due to cost, infrastructure complexity, or industrial inertia. Instead, they were gradually retrofitted, partially modernized, or left in hybrid states where old and new technologies coexisted. The legacy of the boiler room is visible even now in abandoned industrial architecture. Empty powerhouse buildings still stand in former manufacturing districts. Their brick walls are blackened with decades of soot. Their pipe networks hang like skeletal remains. Their control rooms contain gauges frozen in time, needles pointing to pressure levels from the last moments of operation. In some places, rusted boilers remain sealed in place, too massive to remove without demolition. These spaces carry a strange silence, a silence that feels unnatural because it was never designed to exist. It was designed for constant motion, constant heat, constant pressure. Yet what remains is stillness and memory. Modern industry has not eliminated heat-based systems entirely. Large-scale manufacturing still depends on boilers in certain contexts, chemical production, district heating networks, food processing, and energy plants. But modern systems are more regulated, more insulated, and more monitored than their historical counterparts. Safety standards now define pressure limits, maintenance cycles, and operational protocols with precision that earlier generations lacked. Explosions that once defined industrial life have become rare, though not impossible. But even in modern form, the fundamental principle has not changed. Heat is still converted into pressure, pressure is still converted into motion, and motion still depends in part on human oversight. The legacy of the boiler worker is not written in monuments or public memory. It exists in the infrastructure itself, in the buildings still warmed by centralized systems, in the factories still driven by thermal energy, in the industrial foundations of cities that grew under steam. It exists in the unseen labor that once filled boiler rooms with men who measured time not by hours, but by fuel cycles and pressure gauges. And it remains in the historical truth that modern industrial civilization was not only built above ground in steel and glass, but beneath it, in rooms where fire was contained, water was forced into steam, and human endurance became part of the machinery. The boilers may have changed, But the demand for controlled heat never left, and neither did the cost of producing it.